In 2.1, we talked about velocity and finding average velocity versus instantaneous velocity. Now we're just going to tie this into more generic ideas. It doesn't have to be velocity that we're talking about. It can be any rate of change. So this is what 2.2 is about. We are now bringing in this word we refer to as derivative. So let's see what this is all about. So in 2.1, we worked with this ratio where we knew that this was our average rate of change of height or position with respect to time. So this is the change in our distance or position versus our change in time. That was our velocity, and that's how we ended up with kilometers per hour, meters per second, etc. So now we're saying, look, it doesn't have to be velocity. Let's talk about an average rate of change of some function over this interval. Still, we're looking at a and a plus h. So here, a, and if I have this function f of x, my ordered pairs would look like so. A, f of a, and a plus h, f of a plus h. So our difference quotient would just be our change in our y's. So it's our y2 minus y1 over, and then I'm hoping that we are identifying that it's our change in our x's, a plus h minus a. Oh, shoot. A plus a minus, so then that just left us with h. This, folks, is referred to as the difference quotient. All right, so now we're going to take that difference quotient and we're going to knock it out of the park. We are now bringing in what we call the derivative. This is going to be our way of life for the next several months. If I want to find the derivative of a function f at a given x value a, that notation is f prime of a, that little apostrophe symbol, f prime of a. And we define that to be, and we are defining it using our limit definition. This is our rate of change of f at a given point a. It's f of a plus h minus f of a all over h, and we take the limit as h approaches 0. If this ratio exists, if we can come up with a value for that ratio at that given point, we say that this function is, and it's written here, differentiable at a. If we end up with an undefined value, we would say it's non-differentiable at a. So when we talk about the derivative at a point, we have two different ways that we can interpret this. And let's look at both of them just to identify they're saying the same thing. They're saying the same thing. So the derivative at a point A could be referring to the first, the slope of the curve at that given point A. But then begs the question, what does that mean? Well, it means this as well. The slope of the curve at A is the slope of the tangent line to that curve at that point. So let's look at this example that we've got right here. So here's my random point A right there in pink. And here you'll see in green is a tangent line to that curve at that point A, which happens to be the point x equals 3. So if I were asked, what's the slope of this curve at x equals 3, at that x equals a, well, I would then need to find the slope of that tangent line. I can do that by counting boxes. We go rise over run. So maybe we can see that we're going down 1, 2, 3, and over 1. So the slope of that curve at that point x equals 3 is -3. I could have gone this way as well. Up, 3 to the left 1, same thing, right? So that's what we mean when we're referring to the derivative at a point. So if, for example, and this one's not sketched, but if I wanted to find the derivative at that point, okay, that's not good at all. At that point, x equals 4, I would need to find the slope of the tangent line at that point 4. And since it's not greatly sketched, all I can say is that slope looks like it's going to be pretty steep and positive. Now, this might look familiar to you. We did a problem like that in 2-1 that was similar, except it wanted us to find the instantaneous velocity, but now the language is different. The ask is the same, the language is different. They're asking us to find, f prime of 3. What does f prime of 3 represent? It is the derivative of this function when x is 3. It is the slope of the tangent line to this graph when x equals 3. And we are evaluating this initially by using this limit definition of the derivative. And I hope you can see in this wonderfully color-coded setup how we are evaluating this. Here is our limit definition of the derivative. F of a plus h minus f of a all over h, except my a is 3 in this problem, and we take the limit as h approaches 0. In this step, and pause it if you need, we then plug it in to our f of x. So we plug in 3 plus h in red, and we can see that it gives us this. We're going to clean it up next, and then we plug in 3 into the black, into our f of x. And then that takes us to our third step where we simplify, we combine like terms, we cancel out what we can. And you'll see that the 9 cancels with the minus 6 and the minus 3. The 6h and the minus 2h become 4h. And then we're left with that step where we factor out an h, and then we take the limit as h approaches 0, and that gives us 4. So using our limit definition, we have evaluated that our f prime of 3 is 4. So if we're looking at question 6, so these are on the problems that you were given. For 6, when we're just asked, here's our function, and we just want to identify where are those positive slopes, where are those negative slopes. We are just looking at how we're reading that slope from left to right. If it's rising, it's positive, left to right. If it's falling, it's negative. And if it is a horizontal line, 'tis a slope of 0. So now let's look. I'm hoping that if you look at A and you eyeball what that slope might be, if you were to sketch the tangent line, you would say that is a positive slope. Let's look at B. That looks horizontal. B looks like it has a slope of 0. C, what are you seeing? It is a decreasing slope. That's a negative slope. D is horizontal again. That's a slope of 0. And then E, that tangent line looks like it's going to have a positive slope. Okie dokie. So then that's 7 and 8. For 7, we're going to use our graphing calculators. They are asking us to estimate f prime of 3, and we're going to use a table of values, and they tell us what the h, I'm doing quotations, what the h is for that scenario. So let's get our calcs out. So for this problem, we know that we have in our y equals x cubed plus 4x, because that was our function. And then we wanted to use h as 0.001. So now that I know that that's my function, I'm going to quit. And I did a little shortcut so that you wouldn't watch me have to type all of that in. So we did this yesterday where we identified how to call up the y1s. And so my h, you'll see, is 0.001, because that's what they told me to do, right? So I plug that in, I hit enter, and I'm going to round to 3 decimal places, and I end up with 31.009. And the last problem for this, we are given this is 8. This function f of x is a function with this point. And don't lose sight of what the derivative is. It is a rate of change. What is a rate of change? Slope. And then they're asking us to use that information meaning that's all we know about this function. So we're going to use what we know to approximate f of 11. So my hope is that your senses from pre-calc or algebra 2 is thinking, if I have a point and I have a slope, what am I going to use? Point slope. We're going to use the linear equation because that's all we know. We know the point, we know the slope. So I'm going to, here's like refresher, y minus y1 equals m times x minus x1. People, we're going to use this a lot. So make sure you keep that in your back pocket. So here, my ordered pair is 8, 20, and my slope at 8 is 5. So my y value at 8 is 20. My slope at 8 is 5. So let's plug and see. That's y minus y1, which is 20, equals m, that's 5, times x minus, and then my x coordinate is 8. This is all we know right now, folks, about that graph, f of x. So I'm going to use that information. I'm going to approximate what the y value at 11 might be. Here we go. So then that just means I'm going to plug in 11 for x. I'm going to plug in 11 for x. And then I'm going to clean that up, and I end up with y minus 20 equals 15, y equals 35, and we've got it. And lastly, for that problem, just to give you a visual of what we did is and I made this f of x up, but we essentially worked with what we knew, which was the red line. And because we knew that at 8, that y value was 20 and the rate of change was 5, so I know this had a slope of 5, we were able to make an approximation for what that y value would be at 11. So oftentimes you'll notice, and maybe we were a little far off, maybe we were pretty close, we don't know, because we didn't know what the graph of f of x looked like. But with that rate of change and that coordinate, we are able to make predictions. And typically, the closer the x values are to each other, the more accurate your prediction will be. But we can make predictions about what will happen at x values near that given a f of a point. So we can use that to our advantage when we don't know anything else about that function.